All right, we're gonna work out a simple manometer problem. Uh, the figure that you see here, we have a gas inside the container connected to a U-tube manometer with a liquid starting from point 1 all the way to here. We can call point 3, which is open to atmosphere. So over here we have atmospheric pressure. H is the unknown height. We want to determine if gas pressure is given. The equation that we can use is the equation for change in hydrostatic pressure, which is rho g h. Delta P is equal to rho g h. Rho here is the fluid density with the units kilograms per meter cubed. G is the gravitational acceleration with the unit meters per square second. And finally, H is fluid column height. And that should be given in meters. Now let's look at the units for delta P. If we use the units given here, so we're going to have kilograms per meters cubed times meters per square second times meters. Now, let's separate these three units, kilograms, meters per second. This is familiar. It's Newton. And then I cancel this, and I'll have meters squared here. So at the end, I'm going to have newtons per meter squared. This is called a Pascal, which is the unit for pressure. Okay, now let's work out this problem. So starting from left-hand side, we have gas pressure. So at point 1, we do have same pressure as the gas pressure. So P1 is P gas. One might say, well, there is an elevation. It looks like there is a height or elevation change between point 1 and gas. But when you have a gas compressed in a tank like this, because of the low density of the gas compared to the liquid, change in elevation will not contribute to a significant change in hydrostatic pressure. So at point 1, gas P1 is equal to gas pressure inside the tank. So then we move to point 2, and because these 2 points are the same elevation, H is the same, we can write P2 is equal to P1. So now we are at point P2, we want to move up to point 3. So the rule is when you move down, you add. Moving down, you add terms. Moving up, you subtract terms. So moving up from point 2 to point 3, P3 is going to be P2. We have to subtract because we're moving up. P2 minus rho g h. H is the unknown, and in this case, rho is our liquid density. So now we have an equation that relates P3 to P2. We know that P2 is P1 and P1 is P gas. So this can be written as P gas minus rho liquid times G times H. Now we can rearrange this and calculate H. Basically, rho GH will be equal to P gas minus P3. And remember that P3 is equal to atmospheric pressure, so it's going to be P gas minus atmospheric pressure. Right, so H can be easily calculated from P gas minus P atmosphere over rho times G. Okay, there are two possibilities when you want to plug in numbers to determine H. Possibility number one is that when gas pressure is given as a gauge value, let's say 10 kilopascals gauge, in that case you have to convert it to pascals, 10,000 pascals gauge, then H will be calculated as 10,000 divided by, let's say the liquid in the manometer is water and the density for water is assumed to be 1,000 kilograms per meters cubed times 9.8 with G, and the answer is 1.02 meters, the height of the column. So notice that in this equation I did not subtract atmospheric pressure from the given gas pressure because the gas pressure was already given as gauge. So the atmospheric pressure has already been subtracted from it. So the second possibility is that gas pressure is given as absolute pressure. Let's say in this case 110 kilopascals, absolute. And atmospheric pressure, we assume for simplicity that is equal to 100 kilopascals. To be exact, at sea level, atmospheric pressure, standard atmospheric pressure is 101.325 kilopascals. So in calculating H, in this case, pressure given as absolute pressure, I have to subtract it from atmospheric pressure. So H in this case will be 110,000. Remember, you have to convert to pascals, minus 100,000 divided by, nothing changes here, 1,000 divided by 9.8, and you get the same answer, 1.02 meters. So possibility 2, possibility 1, depending on how the gas pressure is given.